Hi again. We will now continue with the topic on turbine. In the previous two videos, we have already looked into the overview or the introduction to turbine, and for this particular video, we will look into the aspect of energy transfer from gas flow to the turbine. Right. The purpose of having the turbine basically to perform energy transfer. The turbine depends for its operation on the transfer of energy between the combustion gases and the turbine. So this transfer obviously is never 100%. Okay, so you don't expect that there will be a perfect or ideal transfer of energy because of the thermodynamic as well as mechanical losses. When the gas is expanded by the combustion process, it forces its way into the discharge nozzles. The first stage of the turbine is the nozzle guide vane. Okay, because of their convergent shape, it is accelerated to about the speed of sound. So basically, the gas will enter at a speed of around 2,500 feet per second. So at the same time, the gas flow is given a spin or whirl. It is rotated, so in the direction of the turbine blades rotation by nozzle guide vanes. On impact with the blades, the energy is absorbed, causing the turbine to rotate at high speed and so provide the power for driving the turbine shaft as well as the compressor. The torque of turning power applied to the turbine is governed by the rate of gas flow and the energy change of the gas between the inlet and the outlet of the turbine blades. So this is the torque or turning power is governed by these two aspects. The design of the turbine is such that the whirl will be removed from the gas stream so that the flow at the exit from the turbine will be substantially straightened out. So it come in with a different whirl or spiral, but it will eventually come out in a, okay, it will be straightened out to give an axial flow into the exhaust system. Excessive residual whirl reduces the efficiency. So, okay, too much whirl will of course reduce the efficiency of the exhaust system. So you want to make sure the flow of the gases that gone through the turbine stage is being straightened and also tend to produce jet pipe vibration. So more whirls mean the nozzle section will be vibrating, and which has a detrimental effect on the exhaust cone supports as well as struts. In terms of the energy transfer, if you look carefully here, a typical turbine blade showing twisted contour. So it has a twisted contour from the root. So we have the root here to the tip. Okay, so it will be seen that the nozzle guide vanes and blades of the turbine are twisted. The blades having a stagger angle and that is greater at the tip than at the root. So if you imagine the direction of rotation showing here, the stagger angle is greater at the tip. Over here, it is larger compared to at the root, which is lower. So this is larger, this is lower stagger angle. The reason for the twist is to make the gas flow from the combustion chamber system do equal work at all positions along the length of the blade, and to ensure that the flow enters the exhaust system with a uniform axial velocity. Let us look at another figure here, which show the gas flow pattern through nozzle and blade, where we have the velocity, profile, and the static pressure. So this results in certain changes in velocity and pressure, as well as temperature occurring through the turbine as shown here. So we have stages of nozzle as well as the turbine blade. How do we read this chart or this figure? Basically, the velocity is being represented by the dotted line. Okay, this is velocity and this is static pressure. So at the nozzle guide vane, the velocity and pressure remain constant. But when it goes through the stage, when it goes to the blade, turbine blades, the velocity will be decreases, and the velocity from this will be decreased, whereas the pressure will be increased from the tip to the root. Okay, and then finally when it passes through, it already have a reduced pressure and velocity. Okay, reduced pressure and velocity compared to the before it enters. So this is before, this is after. Okay, so compared to A and B, okay, where the value of the velocity will be reduced and the value of the pressure also reduced in order for it to go into the exhaust system. The degree of reaction varies from root to tip, being least at the root and highest at the tip. Least at the root and highest at the tip, with the mean section having about 50%. The losses which prevent the turbine from being 100% efficient are due to a number of reasons. A typical uncooled 3-stage turbine would suffer approximately 3.5% losses because of aerodynamic losses in the turbine blades. A further 4.5% would be incurred by the aerodynamic losses in the nozzle guide vanes. We also have a problem of gas leakage over the turbine blade tips and exhaust system losses. So these are of approximately equal proportions. And finally, the total losses result in overall efficiency is roughly about 92%. Now, about energy transfer in brief, we will look into the following video on the construction. Thank you and bye-bye for now.